Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to use this video to have a look at galaxies again and the different sorts of galaxies that we can have in the universe. Now this is not to do with their classification or their type necessarily, this is to do with the environment in which they are found. So this could be a field galaxy, a void galaxy, a cluster galaxy, and why that might actually be important. Now for those of you who may not be aware of what a galaxy is, if you are, then just skip forward basically. These are vast systems of stars, gas, dust, dark matter, actually quite a lot of dark matter, and they're gravitationally bound. So some of these, like disk galaxies that you can see here, will actually kind of rotate a bit like a disk, like the Milky Way. Others have more random motions, but they're gravitationally bound together, and they're enormous objects just full of stars, gas, dust. Some of them don't have that much gas and dust, but still it's a collection of all this stuff basically. These are very big structures. Now there are different types of galaxies which I'm not going to cover here, but just to recap, you've kind of got your spiral galaxies. So if you look at the Hubble galaxy classification system, it looks a bit like a tuning fork. On the right hand side you have these two pathways. The top one is your normal spirals, the bottom one is the barred spirals. Now on some diagrams you have an intermediate one where they're kind of in between a bar and a normal. That just means that they have a weak bar essentially. So in the centre part of the galaxy they have a bar, or they don't. That will give you the pathway. And typically, evolution wise, they're going to evolve from the right to the left. The spiral arms get tighter, more tightly wound. Basically, they lose their gas content because it gets turned into stars, that sort of thing. Then you have your elliptical galaxies. These are pretty much defined by their shape, so you get like an E number for that, and it's essentially how elliptical they appear, and that's pretty much it. Now, these are very different to spirals in the sense that they are not rotating like discs, they don't have spiral arms, they're smoother in appearance, they're redder because they have older red stars. But anyway, we've got these mainly these two populations of galaxies. There are obviously lots of others, but they're the two main types nonetheless. So if we were to look at a galaxy and then we zoomed out, then we can actually start to have a look at the distribution of the galaxies in the universe, because the galaxies are going to be dotted around in the universe, and then we can study that distribution to find out more things about the universe itself. Now if we zoom out far enough, we actually start to reveal a cosmic web. So it looks a bit like this in the background here. And what that's basically telling us is that these galaxies are not evenly distributed. If they were evenly spaced out, as we zoomed out, that would kind of look quite smooth and even, but that's not the case. Now, if we go even further than this to kind of like the biggest scale on the universe, then it kind of gets a bit smoother again. But on this scale here, we've actually got a cosmic web. Now, that cosmic web is made of things like sheets, walls, filaments, nodes. These are kind of high density regions of clusters of galaxies, basically, where you've got much higher density of galaxies than in other locations. So you've got clustering occurring, then you've got areas where clustering isn't occurring, I suppose. And there's various different names and structures that they can be called, kind of down to their shape, I suppose, really. So these filaments are kind of like little like pathways, I suppose, connecting very high density regions. Now, these are some examples of what we might find in the centres of some of these high density regions of the universe. If we zoom back in again to these high density regions, we get these galaxy clusters. And we can also get galaxy groups, which are kind of like smaller versions of this, like 50 galaxies or less. Clusters have an enormous amount of galaxies. So in these regions, you've got a very high density of galaxies per volume in the universe. Now, from all of that, we kind of know that, well, maybe we don't, but most galaxies are not isolated. They're not just in space in the universe on their own. They do tend to cluster in gravitationally bound groups, essentially, which are like your clusters or your groups if it's a smaller version. So we do know that they do tend to want to group. So most galaxies are associated with kind of the higher density regions, like these clusters and groups and stuff. And in the clusters themselves, a galaxy that might be located in one of these, which is kind of like a beautiful picture here, all those different sorts of galaxies there. A galaxy in a cluster is then going to be known as a cluster galaxy. It will be a member of a particular cluster. So this here, this would be a cluster galaxy if we took any of those particular galaxies out there. Now, on the opposite side of the spectrum, we've basically got voids. Now, if we go back to the cosmic web again, these are regions that are almost galaxy-free. They're not quite, but they have very low density of galaxies per volume. So there's a very few amount of galaxies in the same amount of volume that you'd find in one of the clusters. These are called voids. So complete opposite, essentially, of what you'd have in your high density clusters and things like that. Now, in between the two, you've got intermediate density regions, and galaxies located in these regions are known as field galaxies. And they're not quite high density regions, they're not low density regions like the voids, they're kind of in between, but they're still not members of galaxies, and they are gravitationally isolated. So whilst the density is greater than the voids, it's not quite comparable to the cluster environments of the very high density regions. So they still are gravitationally isolated, they're not really interacting with each other, they're still fairly well spaced out, and they're not a member of a particular cluster. Now, why is it important to actually know the galactic environment? So depending on where these galaxies are formed and where they're going to evolve, it actually evolves, or not doesn't evolve, it influences how they evolve. Why would that be the case? Well, actually, in dense clusters, they tend to interact. So if they're dense enough and close enough to one another, they can attract each other, they will collide. That's going to impact how they actually evolve and the end result. We might end up with more larger elliptical galaxies in these high density regions because they've been formed by mergers. Whereas a void galaxy, a field galaxy, is more likely to evolve in isolation and not merge or interact. So it's going to impact its essential life and its end point, really. So it's important to study them in different environments, really. So yeah, basically these void galaxies here, if they evolve independent of other galaxies, there's no interaction going off, you can study that and work out how a fairly typical spiral galaxy might evolve to its endpoint. Is that different to a galaxy that has undergone many mergers and collisions with other galaxies? It's going to help our understanding of the universe and of galaxies in general. So thank you for watching, and if you enjoy the video, then maybe consider becoming a member. There's extra videos in the member section, but it also helps support the channel as well. So thank you for watching.